The ocean roars overhead as nearly 200,000 tons of steel slip beneath the waves. The Virginia-class nuclear submarine, designed for stealth and resilience, dives deep, cutting through the water with a purpose. It descends to depths where the immense weight of the ocean exerts a pressure of over 600 pounds per square inch on its sleek hull. Pressure like this stretches the limits of engineering as the hull is forced to yield, compressing inward by measurable amounts as the sub plunges deeper into the abyss. But why would a vessel designed for deep-sea operations willingly allow itself to be crushed by this tremendous force? Why do these forbidding machines seem to embrace a type of engineering fatigue that would cause most mechanical systems to fail? This episode reveals the mystery of how nuclear submarines crush themselves on every dive. By the end, we will uncover the remarkable engineering that allows them not only to endure this relentless pressure but also to thrive amidst it. As we explore this enigma, it is essential to understand what happens when a Virginia-class submarine plunges into the depths of the ocean. The design parameters of these submarines dictate that they can operate effectively at depths of over 800 feet, where pressure increases significantly with each foot. For context, at a depth of 800 feet, the submarine faces an external pressure that exceeds 600 psi. Yet, while the outer parts of the hull endure this pressure, the interior must remain a safe, controlled environment for the crew and systems to function. The battle against pressure begins at the very design stage of these submarines. Engineers focus on the materials and shapes of the hull. The Virginia-class submarine, specifically, features a 322-foot-long hull composed of high-strength steel, capable of withstanding extreme compressive stresses. This steel construction allows the hull to bend elastically when subjected to immense external pressures. Unlike common misconceptions, submarines do not simply attempt to resist crushing forces, they are engineered to flex, adapt, and absorb pressure without catastrophic failure. Many might assume that the goal is to create a hull that is as rigid as possible, an impenetrable shell that can endure any pressure without yielding. However, that's where the common belief falters. Instead, engineers design the hull to allow controlled deformation, extending its fatigue life. It's a brilliant counterintuitive approach. Rather than fighting against the crushing pressures of the ocean, they harness it. By allowing the hull some degree of elasticity, engineers can minimize the risk of damage over repeated cycles of immersion and resurfacing. This is where it gets fascinating. Submarines experience not just a single instance of pressure while diving. Think of it like putting a heavy load on a hill. If you lean too hard, you risk slipping. But if you gently shift your weight and allow the load to distribute evenly, you can safely navigate the slope many times. This flexible approach allows submarines to cycle through dives repeatedly, absorbing an immense amount of pressure without significant structural compromise. Now, take the USS Virginia, the lead ship of its class, commissioned in 2004. This submarine is a prime example of cutting-edge design. Certified to operate down to 850 feet, it embodies the marriage of technology and innovative engineering, demonstrating how a well-calibrated hull structure can endure while also adapting to the pressures of the deep sea. This careful engineering is not just an academic exercise. The necessity for such resilience was starkly highlighted during testing in the mid-1960s with the USS Thresher, a submarine that tragically failed during a deep dive. The investigation revealed that significant structural failures resulted from improper understanding of pressure effects on submarine hulls. This led to an evolution in design philosophy among naval architects, an emphasis on not only resisting external pressures but also accommodating those pressures. As we consider the forces at play, it becomes apparent that these submarines are constantly transitioning between pressure extremes. During ascent and descent, the hull undergoes repeated cycles of loading and unloading. With each dive and subsequent rise, stress accumulates. Engineers estimate that a Virginia-class submarine can undergo thousands of dives throughout its operational lifetime. This wouldn't be feasible if their constructions didn't account for repetitive stress. It's a deliberate choice made by engineers to embrace the crushing forces of the deep rather than wish them away. So, you may be wondering, how exactly does this work in practical terms? To give you an idea, imagine walking on a trampoline. When you step onto the surface, it bends and flexes beneath your weight, but it does so within calculated tolerances to ensure you stay suspended above the ground. Similarly, submarines like Virginia are designed to let their hulls flex within a narrow range of deformation. This enables them effectively to distribute the pressures they encounter underwater evenly. Interestingly, when the submarines dive, the outer layers of the hull compress while interior layers maintain a safe pressure that ensures the integrity of the compartments. A remarkable balance is struck, preventing overstress conditions from developing. To achieve this, engineers frequently utilize thick-walled structures and specific geometric shapes that allow for adaptive responses to varying depths and external pressures. In addition to resilience, these shapes contribute to reduced drag, improving overall performance during transit. As we reach our midpoint, think about this: which of these machines would you least want to be standing next to? A conventionally powered boat resting on its anchor, a heavy oil rig floating atop the waves, or a nuclear submarine silently gliding into the depths? Let us know your thoughts below. But now we delve into a surprising twist in our exploration. A common misconception exists that submarines rely solely on their materials for strength and durability. Everyone assumes that thicker is better, however, the opposite is true in some respects. The engineering philosophy that governs the Virginia-class submarines embraces the idea of strategic flexibility rather than rigid strength. The hull doesn't need to be invulnerable, it must be smartly designed to yield within parameters. This leads us to the conclusion that the secret of these vessels does not lie in brute strength but in introspective design. The Virginia-class submarines have incorporated failure analysis and advanced computational simulations into their structural assessments. Engineers use high-fidelity models to predict the life cycle of stress and fatigue, identifying the points of maximum strain while also creating configurations that allow the materials to cope with adversity. As these submarines continue their missions, the engineering behind their hulls remains a hidden marvel of ingenuity. Excelling at depth, the Virginia-class boats exemplify a nuanced understanding of the environment they operate in, facing extraordinary pressures while continuing to protect and serve. In closing, it is awe-inspiring to reflect that within the great depths of our oceans, our most formidable machines carry secrets untold. The art of engineering behind submarines like the Virginia-class teaches us that sometimes embracing pressure rather than resisting it can yield the most resilient solutions. They remind us that the machines that traverse our world are often far stranger than they appear at first glance. The machines that move the modern world are stranger than they look. Subscribe, and we will take apart the next giant together. As we delve deeper into the technological marvels of the Virginia-class submarine, it becomes crucial to examine the myriad intricate components that work together to manage the external forces at play. The Virginia-class submarines incorporate advanced technologies that enhance their capability to withstand crushing underwater pressures, ensuring both performance and crew safety during their lengthy missions. One significant component of the Virginia-class design is its advanced hull form. The hull's shape is not merely aesthetic, it is a finely engineered sculpture designed to minimize hydrodynamic drag while maximizing structural integrity. The shape resembles that of a fish, with a teardrop profile that allows it to slice through water efficiently. This design reduces the potential for turbulence that could exert additional stress on the hull, ultimately preserving the integrity of the vessel as it descends and ascends in various oceanic conditions. Even slight discrepancies in shape can lead to performance issues, making precise engineering vital. Let us consider a practical example. The USS New Mexico, a Virginia-class submarine commissioned in 2008, is notable for demonstrating the potential benefits of this design philosophy. During exercises, it reportedly operated at an unprecedented maximum depth of 860 feet and performed flawlessly, highlighting the effective use of geometry and material physics to endure conditions that might lead to failure in a less resilient structure. To further mitigate stress caused by external pressure, engineers employ sophisticated computational fluid dynamics (CFD) analysis during the design process. This method enables them to study how water flows around the submarine's hull at different angles and speeds, refining the design to ensure optimal fluid movement. In essence, CFD analysis allows for the simulation of thousands of dives without ever leaving a laboratory. This thorough testing process ensures that when a submarine enters real-world conditions, it is equipped to handle the stress dynamically and efficiently. Additionally, the use of high-strength steel goes beyond mere compliance with engineering specifications. It encompasses a careful selection process that ensures the right balance of strength, weight, and water resistance. The steel used in the hull is not just any steel, it is often specially formulated to display an impressive yield strength of approximately 130,000 psi. By incorporating such advanced materials, the overall strength of the hull is fortified against both the stresses of water pressure and the corrosion associated with long-term saltwater exposure. Let's take a moment to reflect on another major consideration, the submarine's internal pressure versus external pressure. Internally, the submarine maintains a pressure of about 14.7 psi to ensure crew members can operate safely and comfortably. The stark contrast between internal and external pressures creates an interesting engineering dilemma. The submarine's design must accommodate not just the external pressures but also manage the stability of its internal compartments against this extreme difference. To illustrate how this disparity is handled, consider the American USS San Francisco, a Los Angeles-class submarine that struck an underwater seamount in 2005, sustaining significant hull damage. The incident highlighted the importance of not only resilient hull design but also effective pressure balancing. While the Virginia class has improved upon its predecessors, the lessons learned from such events have been invaluable for continuous design improvements. Moreover, the concept of controlled deformation within the hull applies to internal structures as well. Submarine systems, like propulsion and power generation, must endure different pressures. The integrating of flexible mountings and shock absorbers into critical systems allows them to operate without transferring undue stress to the hull. This method ensures that components remain functional even if the hull experiences cyclic loading and unloading during dives. As we explore further, it is essential to appreciate that effective sound damping technologies are also paramount. Submarines are designed for stealth, and sound travels extraordinarily well through water. Engineers employ a range of materials to dampen sound transmission from the hull and internal systems. Acoustically treated surfaces, strategically placed sound-absorbing foam, and even the careful selection of the shape and location of machinery help minimize noise. This design choice not only aids in maintaining stealth but also reduces the strain on physical structures by lessening the inherent vibrations caused by machinery during operation. Impacts from external vibrations, such as those generated by turbulent water flows around the hull, can foster critical fatigue over time. As such, the Virginia-class subs are fitted with vibration isolation systems that help address these issues. These systems are akin to the way advanced car suspensions manage the dynamics of driving. By ensuring that vibrations are mitigated before they reach sensitive systems or structural elements, the longevity of both equipment and the hull itself is enhanced. In fact, the balancing act of managing stress on the hull is not only a product of physical engineering but also of real-time operational protocol. Crew members aboard submarines undergo extensive training to recognize and respond to changes in pressure and depth. They monitor vital systems continuously, ensuring the hull remains intact and the crew is safe. As we near the end of our exploration, it's important to consider the lessons learned from historical accidents. The USS Scorpion, which tragically sank in 1968, revealed grave consequences associated with hull integrity in extreme conditions. Investigations into the ship's wreck underscored the importance of robust design and reinforced our current understanding of how pressure affects submarine performance. Following this incident, submarine designs since have seen significant improvements in how engineers approach hull sizing, material selection, and adaptive measures to account for the drastic changes encountered during operations. Additionally, we cannot overlook the role of technology in this story. Engineers employ advanced sensing technologies, such as fiber optic sensors embedded within the hull materials to monitor stress levels continuously. These sensors provide real-time data regarding how much compression the hull sustains during dives. If certain pressure thresholds are surpassed, alerts can be generated on board, allowing crew to respond appropriately and adjust course if necessary. This proactive approach underscores a commitment to safety while maximizing operational capabilities. As we reflect on the remarkable resilience of submarines like the Virginia class, we find a microcosm of human ingenuity and adaptability. While the immense pressures of the ocean pose threats to these formidable vessels, they serve as a reminder of how thoughtful design, technology, and engineering principles can work together to overcome adverse conditions. Such adaptability is not confined to submarines. It echoes throughout the marine engineering industry, inspiring innovations in pressure resistance across landscapes, from underwater infrastructure to deep-sea exploration vessels. In closing, it's astonishing to realize that within the crushing depths of the ocean lies a realm where engineering challenges not only exist but are routinely triumphed over through the very philosophy of design itself. By embracing pressure instead of resisting it, engineers have developed submarines that exemplify resilience and intelligence. They remind us that the complexities of our world are often hidden beneath the surface, waiting to be understood.